Here we go. Gases. Gases and thermo. We talked about this at the beginning last time, about the importance of gases in thermodynamics. And the key thing was that a gas can expand and contract, and therefore you can do work on the gas and compress it, or the gas can do work for you and expand. Okay? So that's the key on why gases are so important in thermal physics. So, since we're using gases, okay, or gases in thermal. Okay, that brings us three exceedingly important things. All right? Okay, number one, if we're dealing with gases, then we will be using PV equals nRT. So remember that. Keep that in your toolbox. I'll write it up over here. PV equals nRT. Very important for what we're going to be doing in gases. Okay, second thing. Okay, now we talked about this with gas laws already, but since we know that a gas only has kinetic energy, and the kinetic energy of a gas is related directly to the temperature, remember we had this, that the average kinetic energy was 2/3 or 3/2? Do you remember? 3/2. K, B, T, right? Boltzmann's constant times temperature, correct? Okay, and then we took that and we said, look, we can make this into the total energy of the gas. We just multiply by how many gas molecules we have, right? And we converted that into this. U equals 3/2 nRT. Okay? We're only going to do one slightly new step. So we've already covered all this. One new step that gets us to where we want to go for thermodynamics. Remember, in our thermodynamics, our big law is the first law of thermo. And remember, the first law of thermo is nothing more than extension of conservation of energy, right? You remember what our first law of thermo was from last time when we derived it?
The change in thermal energy is equal to heat transfer plus work.
Very good. The change in internal energy of the material, whatever it is equal to how much heat you put into it plus how much work you do on it. Okay? So, how do I change this to give me that? Alright, I want to change this to delta U. Well, the 3/2 isn't going to change, right? R is certainly not going to change, right? So that's a constant. Okay. If we assume we keep the same number of moles of the gas, alright? Then it'll be change in temperature, right? Now, if you want to be most precisely, it's delta U equals delta 3/2 nRT. But the only two that can change would be the number of moles and the temperature, right? And in most cases, it's the temperature changing and not the number of moles of gas. Okay? So this is an assumption that only the temperature will be changing. Alright? But that's usually a pretty good assumption. So in gas laws, we got this from kinetic theory of gases, and then we converted it to this when we multiplied by how many molecules we had. So this is the total energy inside the gas. And this is how much the energy of the gas changes if we're changing the temperature. Okay? So there we go. So we just figured out how to find that. So, add that to our list. We've got delta U equals Q plus W. We have PV equals nRT. And we have delta U equals Q... No. Thank you. I started to write the same one over again. Equals 3/2 nR delta T. Alright? Okay. Last thing, since we're dealing with gases, that makes this... The interesting thing about using gases in thermo, okay, is how we figure out work. Okay? Work equals the change in energy. Well, we've expanded that, haven't we? Work no longer equals the change in energy of the system. Because work is only one of the things that changes the energy of the system, right? Now we've added a new thing that can change the energy of the system, right? Heat addition. So when we're talking about mechanics, work equals the change in energy of the system. But now we're adding Q. So let's go back. What's our basic definition of what work is? What's our equation for work?
D cosine.
Very good. FD, or delta R, cosine theta, right? Okay. Now, I'm going to do something that you do in math class all the time. I'm going to multiply by an area and divide by an area. In math class, if I multiply and divide by the same number, then it doesn't change anything, right? Okay, but I'm going to rearrange this. I'm going to have F over area. Then I'm going to have a delta R times an area. And then I'm going to have a cosine theta back out here. Okay? Very nice. This is a pressure. What's delta R times A? It's slightly more than volume. Because there's a delta, right? So it's a change in volume. This is a change in volume. So, change in volume. Very nice. And then we have a cosine theta. All right? Now I'm going to get rid of the cosine theta. All right? When you have a gas and it exerts a pressure, all right, which direction does the gas exert pressure on this wall? This board up here?
Against the wall.
This way, right? Which way does the gas exert a pressure on the ceiling? Straight up. Very nice. The pressure in a gas is always, or the force because of the pressure, is always perpendicular to the surface. So like for me, right now, when I'm standing here, okay, there's pressure all over me. And the pressure right here is this way. And the pressure right here is this way, right? So that it's always perpendicular to the surface, right? Right. Okay. Now, if the pressure is perpendicular to the surface, yeah. If you got a container, it's filled with a gas, and let's just look at the right side. If the force, because of the pressure, is this way, okay, and it's either going to expand or contract, outward or inward, it's only going to move this way or this way, then their cosine theta is always going to be either 1 or negative 1, right? So it's always going to be 0, cosine of 0, or cosine of 180, right? So there's going to be 1 or negative 1. So this I'm going to get rid of. So it's always going to be 1 or negative 1. So we just have to figure out what's our sign convention. Work equals pressure delta V for a gas. So I'm going to put gas down here because this only is good for a gas. Okay, so what is our sign convention from last time? If, remember, this is my system. Here's my gas. And let's say there's a pressure here. So the pressure is going to be outward from the gas. Okay? And let's say the pressure... Can the pressure be negative?
It can only be pressure from the other side.
You can't have a negative pressure. What's the lowest pressure you can have? Vacuum, right? 0 pressure. So pressure is always going to be positive, or at best, or as low as 0. Okay, and then if the gas expands, that's going to be a positive volume change, right? So pressure is positive. If I have a positive volume change, now wait, let's go back. If the gas expands, is the gas doing work?
Yeah.
Or is the environment doing work? The gas is doing work, right? The gas is doing work on the environment, moving the environment out of the way. Now wait a minute. If the gas is doing the work on the environment, moving the environment out of the way, like if you're standing here and you push the people around you away, you're doing work on them, who gets the energy? They do. Where did the energy come from? So what happens to the energy of my system? It goes down. So what happens to the energy of the system if the gas does the work?
Goes down.
It goes down. So remember, by our sign convention then, work done on the environment or work done by the gas, that's the same statement, that's considered to be negative, right? So here we go. Here's our sign convention. This is really important. This is where students get this mixed up. It's kind of confusing. Because we always have a positive pressure, and if we have a positive volume change, right, then that would make this number over here positive. But by our definition over there, that's going to lower the energy of the system, right? So that's considered negative work. Okay? I'm going to let that sink in for a second. Whenever the gas does work, that's considered negative because it's going to lower the energy of the system. All right? That's correct. So when the gas expands, that's negative work. When the gas contracts, that's positive work. Very good. So we're going to write that down to help us out. So work equals negative P delta V. I'm going to move my negative to the right. Okay? So you get positive work when gas contracts. You get negative work when gas expands. Okay, does that make sense? That's the hardest one of the batch to remember, I think. But you can do it. Just have to think about it.
So, the work is done on the environment or done by the gas, and it's negative.
That's correct. If work is done on the environment or work is done by the gas, that's negative. Very good. I know, it's like there's like about 4 or 5, 6 different ways you'll hear the same thing, and you just got to be able to pick that out. The heat added or subtracted from the gas, I think, is a piece of cake for everybody. All right? So there we go. That's our big toolbox for most everything we need to know. All right? So there we go. We got gas law. We've got how to figure out the internal energy of the gas and how to figure out the work. Okay? And then there's our first law of thermo. And what's our 0th law of thermo?
If one object is at equilibrium with another, and if that object is at equilibrium with another, then the first is
Let's do markers.
Yeah, if you just remember, here, we'll do markers again. If the black marker is in thermal equilibrium with the blue marker, and the blue marker is in thermal equilibrium with the green marker, then you can say that these two are in thermal equilibrium. Or you could say, if temperature black marker equals temperature blue marker, and temperature blue marker equals temperature, I said yellow, green marker, then the temperature of these two are the same, right? It's the same statement. It's essentially, it's like A plus, if A equals B and B equals C, then A equals C. All right. So now we get down to the fun part.
All this writing.
All this writing. So what we have so far is all the basic stuff, all that gas law stuff we talked about, and how to figure out work for a gas, how to figure out the internal energy for a gas, first law of thermodynamics. Well, how many different variables are we trying to keep track of? What do we got? We got delta U, right? We've got Q. We've got W. So the internal energy of the gas, the heat added to or subtracted from the gas, the work done on the gas or by the gas. We've got pressure, volume, number of moles, temperature.
What about R?
R is a constant. So we'll let that one go. Same with Boltzmann's constant, K sub B. All right? Okay, but look. This equals Q plus W. And this equals negative P delta V. But this right here also equals 3/2 NR delta T, right? So wait a minute.
They're all
All of this stuff all comes from this one, this one, this one, and this one. Because if I know those 4, I can find work,
And R.
and I already know R. So I can find delta U. And if I know the change in internal energy and I know work, I can find Q, right? So with really all those things, all I really need to know are those 4 things about a gas, right?
What is Q again?
Q is the heat. And heat is positive when it's added to the gas, because that raises the energy of the gas. Very good. So these are the 4 things. We're still back to gas laws again, aren't we? PV and N and T. All right, so let's find a way to keep track of these 4 things. All right, when scientists or engineers have too many things to keep track of, then generally they'll find some way, some method for trying to figure out what's going on. And so the way they chose to do this is they chose to have a graph called a PV diagram. Okay? On my PV diagram, what's on the vertical axis? Pressure, which would be in pascals. Hey, by the way, I will give you this caution. Be very careful. Since Pascal is a small unit, sometimes they'll do things like this. They'll go times 10 to the 5th pascals. And then over here they'll do this. 0, 1, 2, 3, 4, 5. So that means right here we're at what pressure? 400,000. They just do that to make it easier to write this axis. Okay, so just be careful. Over here we have volume. Just be careful over here. A lot of times they'll do things like this. Times 10 to the negative 3rd meters cubed. And then they'll go 0, 1, 2, 3, 4, 5. Okay? So right here we're at 3 times 10 to the negative 3rd meters cubed. Because meters cubed is a pretty large unit for volume, right? Okay, what's that?
That's 3 liters.
Ooh,
3 10 to the negative.
isn't it 3? No, 10.
That's 3 liters.
That's 3 liters? Oh yeah, whoa. Yeah, because it's
0 to
10, 10. Yeah, it's 3 liters. That's right. That's right. Very good. All right. So here you go, everybody. We're going to keep track of all our things. So let's go right here, and let's say we're right at this spot right here. There's the spot we're at. That's the state that our gas is in. Okay? So what's the pressure of that gas? How do I find that? You go like, you start there, and you look this way, and you read the graph. Amazing.
Hey, that's easy.
So we have 400,000 pascals. All right, and now I want to know the volume. How do I find volume?
Go down, 3 liters.
You go here and you look this way, and you go, hey, the volume is 3e to the negative 3rd meters cubed. Excellent. I know, this is a piece of cake. And then we say, well, wait, I want to know the temperature of the gas. Let's solve for it. How would I solve for it? Very good. PV equals nRT. I'd put in 400,000 pascals. I'd put in 3e to the negative 3rd. I'd put in we'd have to know how many moles, right? So the number of moles will have to be given. So let's say that the number of moles is 2.
0.6.
Okay? 2.6?
What is this?
All right? 2.6.
Oh my God.
Come on, you have a calculator.
I'm actually doing the math.
I know, right?
Oh, baby.
You have your calculator, right?
Yes, sir.
All right. By the way, just as a word of caution, sometimes the question will start a mole of gas, and then they'll go on in the problem and describe other things. And if they say a mole of gas, they just told you how many moles of gas, right?
2.
2. 1. All right, so let's say this is 2.6. Okay, R is 8.314 8 dot pi joules per mole Kelvin, and then we find the temperature. All right. Practice. What's the temperature? You have 30 seconds. Go. Find the temperature. Check it with your neighbor. That's a solid state processor calculator. It's not. Doesn't have tubes that need to be warmed up.
Yeah, it does. Found it.
Yeah, you gotta crank it up. You check with your neighbor.
Here. Hey,
Oh, I'm still in.
Who needs a calculator?
Hey, the hamster said I was right.
Calculator.
Would you get rid of
55.
Calculator. Calculator. Come get your calculator.
55?
That's my
It's already being
Anybody else?
Yeah, I think so. Either actually.
All right. So what's our temperature? 55. Oops. 55.6 what?
Kelvin, it's 56.
Oh, it's 56.
Or 55.5. Yeah.
All right.
Because if we are, then
Yeah. If we're doing sig figs, we're in trouble, right?
6.
Yeah. Actually, if we were doing sig figs, it would be 60, right? Okay. We'll assume we got 2 sig figs since I'm just making these numbers up. All right. So around 56 degrees Kelvin. Actually, you don't even need to say degrees, really, technically. You just say 56 Kelvin, right?
Yeah.
There you go. Hey, that was easy. All right, now, let's say that I move this way
what if it's a curve?
to point A. I'll get you there in a second. If I move from the original point, which we'll call O, the origin, to A, what happened to my temperature? We have a vote for it goes up. Do you concur?
Yeah, it increased.
Yeah.
Sure?
Yeah.
Why?
If you increase your volume,
Wait, no, it's going to be.
All right, now look at our PV equals nRT, right? The volume increased, assuming that stays the same, and that always stays the same, and well, pressure stayed the same, so temperature has to go up. What other directions could I move it? I could move it straight upward.
On the slope.
oh yeah.
I could move this way to point B, and the temperature would go up. Or I could move on a slope, like that slope. I could move it along this direction to point C, and all of those, the temperature will rise. Which way would I move it and the temperature would decrease?
Going down to the left.
This way, and this way. So all of these, it gets colder.
And if it's the other two, it's
hot.
And all of these, it's hotter.
What about the other direction?
Okay, that was my
depends on
question.
how much you.
What if you go this way or this way?
It depends on how much you change.
It depends on the slope of the line.
You know, if your pressure.
Depends on how much you use pressure.
Yeah. What if I double the volume and I cut the pressure in half? Then it would be the same. So there's going to be somewhere along in here. There's going to be a location where it's exactly the same, right? Okay.
What's the name?
It's not like that. I'm checking.
Is it originally Staples?
I don't know.
No. It doesn't have anything in there.
Okay, let's try this thing. What is this chain?
I know.
Who wants this
It's
thing?
like we're in a ghetto school. I jacked this thing.
This one time I went to the orthodontist and there was like there was a guy from jail there. He was in Gainesville and he was like a bajillion chicks. He was like strapped to the end of the car.
Oh my god.
And then he had 3 police officers around him.
And he was here.
And then there was 2 police officers. There was 2 police officers around him. Oh yeah. I was like, dang, what did he do? Kill somebody? He's got bracelets.
All right. Now, look at the board.
there's the first one.
A, B, C, D, and E.
Why not?
Wait, what is the bracket? I don't have
Is A supposed to be on line 5?
Yes.
And is B
This
supposed to be
one?
on 4? You can't draw a straight line.
Yes, you can.
All right, now, tell me which one's the hottest. Rank them in order from hottest to coldest.
Right here.
They're all the same.
Not the same.
No, they're not.
They're all relatively so.
They're all relatively the same. Boo is.
The hottest, A, C are the same, and D.
You're such a cheater.
What is the hottest? I didn't read it.
But remember, that one has a point extra than the one here, and they're at this.
I didn't cheat. I didn't even look at the end of the side.
A's the hottest because.
No.
Because my last time was out of set.
No, you just multiply the two numbers. Multiply
B and C are the hottest.
number, and that's
And then D and F are the second highest. And then E is the
B or C.
Okay, explain yourselves. How are you ranking them? How do you know if it's hot or cold?
Pressure times volume.
Right.
Okay, pressure times volume determines my temperature, correct?
Yeah.
Because if the number of moles is staying the same and the universal gas constant stays the same, then my P times V value determines my temperature, right?
Yes.
And so this one right here has a P times V value of 10 PV. This one has a 12 PV. This one has a 12 PV. This one has a 10 PV. And this one has a 6 PV. So in order from hot to cold, you have B and C are the same, A and D are the same, and then E. Right? Now, what we have here is we have spots that are exactly the same. Okay? Now wait. We just said that every time we have a P times V value gives us the same temperature. If this is the same and doesn't change, this whole side becomes a constant, right? If P times V equals a constant, what shape on the graph will that be on a PV diagram?
Memorize these last year.
Okay, will it be slanted? Well, here's a straight line slanted. Are all these the same temperature?
No, sir.
So they have to
Horizontal? No, it can't be horizontal because the pressure stays the same, but the volume increases. That won't be constant. Like this? You start at 0, 0 and you go up? That won't work because that means that it won't be constant. Ah, I'll give you a hint. If this was an X, Y graph, and I said X times Y equals a constant, or that would be Y equals a constant over X. What kind of curve is that?
inverse.
That's an inverse graph, right? Which is exactly what you said. It goes like this, right? Whoosh, right? Like that. So this, what's the name of that curve? What's the name of that curve in algebra or geometry? It's an inverse curve, right?
Yeah.
Oh, come on, you've heard it. It's a conic section.
No, we haven't heard that.
It's not a circle. It's not an ellipse. It's not a parabola. It's a hyperbola. Very nice. So this is a hyperbola. Hey, that means that these two are on a hyperbola. That means these two are on a hyperbola. If I can draw it.
And D's all.
And this one.
And DV is all.
And that's on a hyperbola. This is the 12 PV hyperbola. This is the 10 PV hyperbola. This is the 6 PV hyperbola. Now that will relate to a temperature. So this will be a hot temperature. This will be a colder temperature. So this might be like the 600 Kelvin hyperbola. This might be the 550. This might be the 300. Okay? So there's going to be a whole family of hyperbolas on this graph. So when you have a PV diagram, I want you to visualize a whole bunch of hyperbolas in here. Each one of these hyperbolas has its own temperature, where hot is out this way and cold is down this direction. And absolute zero is right there, if there's such a thing, right? Okay, so hot's out that direction. Cold's down in this direction. Okay? Excellent. Okay, now we had a question about what if we traveled along a curve? So the question I think was, all right, if I go from the origin to A along this path, but what if I go from the origin to point A along this path? You ready? Here's my path.
Oh, gee, come on.
Okay, there's my path from the origin to A. Okay, if I go from the origin to A along this path, the straight path, does my temperature go up or down? Up. If I go from the origin to point A along this straight path, this path right here, temperature go up or down? Okay, if I go from the origin to A along this curvy path, is the temperature going up or down?
Still up. That changes still up.
Now, here's my question. Has the change in temperature changed, or is it the same? Does the path matter?
No.
Not from beginning to end. Okay, everybody? Here's the deal. From beginning to end, all we care about is not how we got from one spot to the other, but just the initial spot and the ending spot. And those determine my change in temperature, right? Because this spot has a certain P times V value, and this spot has a certain P times V value. And how I get from here to here makes no difference for the temperature, right? It's just where I'm located. Does that make sense?
Yeah.
Okay. Now, taking a different path does make a difference for some things, but not for temperature. For temperature, all that matters is where you're at. Okay? All right. So let's say you start here at point 1. You go out to point 2. You go this way to point 3. Oops, 3. And then you go this way to point 4, and then this way back to point 1. Okay, going from 1 to 2, has the temperature gone up or down? Up. Going from 2 to 3, temperature gone up or down? Down. How about from 3 to 4?
Same.
Up, down, or the same? Same, because you're along the hyperbola, right? Now, the only way to know if they don't draw a hyperbola for you,
You can do it.
then you could determine it by doing what? Multiplying the P times V value here, and the P times V value here, and if they're the same, then it's the same temperature, right? Okay, what happens when you go from 4 back to 1? Goes back up. What if you start at 1 and go to 2 to 3 to 4 and back to 1? What's the change in temperature?
The 1 to 1 is
None. From 1 back to 1, you're back where you began, right? It's kind of like displacement, right? If I start here and I go over here and then I come back, I've moved a distance out and a distance back, but my displacement is 0 because I'm back where I began. Okay? By the way, as you go all the way around, that's called a cycle. If you go all the way around back to where you began, that's called a cycle, and the change in temperature is 0. Okay, now, trick question. If I go from 1 to 2, has the internal energy of the gas gone up or down, or stayed the same?
Yeah, temperature went up, which is pressure and volume.
It's going down.
So it did go down.
It's
Okay.
going down.
Very first thing you do is find the relationship that tells you how change in temperature relates to change in internal energy of the gas. That's going to be this equation, right?
Yeah, and that's constant, assuming.
So 3/2 is a constant, R is a constant. We're assuming the number of moles isn't changing.
So it's good.
So look, if the temperature changes, then the internal energy of the gas changes exactly the same. Well, exactly the same direction, but it'll be a different number based on these constants here, right?
Yeah.
Okay, so when I go from 1 to 2, temperature change from 1 to 2 is positive. So internal energy change from 1 to 2 is also positive. So pick out all the processes here where the internal energy of the gas goes down.
From 2 to 3.
We got to vote for 2 to 3. Do we agree?
Yes.
How do you know?
Because 2 to 3 goes down.
Because the temperature goes down from 2 to 3. Are there any others besides that
That's a
one?
4. Can we go, or we just have to go down?
You either gonna, or you have it.
Oh, you're saying if we went from 2 to 4?
No, yeah, from 1 to 4.
If we went from 1 to 4, if we went backwards, then yes. But if we're going the way I drew my arrows, is there any others?
No.
Okay. We go up in temperature, down in temperature, same temperature, up in temperature. Okay? So the only one that I've drawn that is a change in temperature that's negative, which means a lowering in internal energy of the gas, that's from 2 to 3. Okay? Excellent. Very nice.
That's it.
We just figured out how to find temperature and change in internal energy, which gives us delta U in our first law of thermo. Excellent. So now, let's figure out how to find work. Work. What? I just labeled my graph work. That wasn't no good. All right. PV. All right. Hey, our equation for work. Work equals negative pressure times change in volume. Okay, so I started right here, and I'm going to move from here to here. Okay.
No.
How will we know if we have work? Do I have work? Is that work?
Yes.
Why?
Because we have changing
Changing volume.
Because I have a change in volume and I automatically have a pressure, right? So there's a pressure and there's a change in volume. So I have work. Ooh, question is what kind of work? Is it positive or negative work? Which one's doing work? Is the gas doing work or the environment?
Well,
The gas is doing work. So that would be negative work, right? So this is negative work. Okay. What if I'm right here and go from here across to here?
still negative.
It's still negative work, but is it the same magnitude of work? Why less?
Because the pressure.
volume change.
Okay, so I have the same volume change, but a different pressure.
Yeah, lower pressure.
So I got a lower pressure, so I have a smaller amount of work. And if I'm up here and go across, then I'll have an even greater amount of work, right? Okay, all right, calculus tie-in. You ready?
Yeah.
In reality, work equals the negative integral of P dV.
All right.
Alright, I'm ready for this.
You ready for physics C?
Oh, that makes sense. I'm not even ready for.
Go, let's do it.
Okay, now, integral. What is the physical manifestation? What does integral mean on a graph? It means area. So what this really means is it's the area under the PV graph. Now you got to be careful though. That way, directions to the right are negative work. Directions to the left are positive work because of our sign convention. So, you see this area here? That's a little bit of work. You see this area here? That's more work. You see this area here? That's the most work, right? Okay, when you think of it in terms of area, sometimes it makes a little bit more sense. So, PV. What if I start here and I go from, well, you know what? I'm going to save that one. I'm going to save that one. Let's do this. Let's say I start here at O again. Which ways will I have to move from that spot in order to, well, back up. What if I just stay right there? Is there any work?
No.
Okay, so I have to have movement to have work, right? Okay, which way can I move from that spot and have positive work? To the that way, right? Okay, so that. Actually, how about that? Okay, are all those the same amount of work? All right, so this one is a lot of positive work because there's a big pressure and a change in volume. And there's a negative sign here, but I have a negative change in volume, right? At this one, I have an intermediate amount of work because I have an intermediate pressure and I have a same change in volume. Down here, I have a tiny amount of work because I have a smaller average pressure but the same change in volume, right? Or you can think of it in terms of area, for those of you that like that idea. If you go underneath all these, it's easy to see that this area is the smallest, this area is bigger, and the area underneath the top graph is the biggest, right? So you can think of it different ways, whichever way is most convenient to you. Okay, is there a way to move from the origin? Wait a minute. Which way do I move from the origin to get negative work again? To the right? So I get negative work going this way, positive work going this way. Is there a way to move from the origin and not get any work? What if I do that? Do I have pressure? Yes. Do I have a change in volume? Ooh, so do I have work? Or if you think in terms of calculus, is there any area underneath this line? No area there, is there? Okay? So, all right, you ready? Here's this general rule of thumb for work. Pressure, volume. If you move that way, that way, that way, it's all negative work. Okay? In fact, I'll draw it like this. A big negative work, less negative work, tiny negative work. If you move that way, or that way, you have big positive work, or a little bit of positive work. Oops, I wrote negative. Positive work. And if you move up, straight up, or straight down, work equals 0. Okay? So you have to have movement, but you have to have a change in volume. So you're either moving to the left for positive or to the right for negative. Okay? Okay, so let's go back and see if it makes sense. What if I start right here, point A, and here's point B. And I move this way to point B, or I move this way to point B, along path number 1 or path number 2. Okay, tell me, is the change in temperature the same or not? Is the change in internal energy the same or not? Is the work done the same or not? Well, let's think about it. Temperature change the same? Yes, they're the same. Because all that matters for temperature is, do I start and end at the same PV values? So, is my temperature going up or down?
It depends.
I don't know, where's your baby?
I don't know. Where's your parabola? That sounded awfully whiny.
Hyperbola thing.
Where's the hyperbola? I didn't draw a hyperbola. Hey, can we tell definitively? That's a college word. definitively, if the temperature going along path 1 or path 2 is going up or down or staying the same? We can't really tell because our pressure's going up, which would raise temperature, but our volume's going down, which would lower temperature, so we don't really know. We just know that along this path and this path, the temperature change is the same. So how about internal energy change?
Same.
It's got to be the same, right? How about work? Is work the same?
No.
Yes.
Yes. The change in volume.
It is the same.
No.
It's the same. It is.
Work equals pressure
Area
times
change in volume. Change in volume is the same pressure. dV. Derivative of
It's the same.
Well, I'm just saying this is what she said.
It's the same because they're all at the same spot.
You had it all right except for your reasoning.
Because they're all in the same spot.
You're right. It is the area under the curve, but the area
It's from A to B.
See?
is either that
You got like your shot, man.
or that.
Make it.
Nothing.
So is the work the same?
Oh.
The work is not the same. Which one has a bigger magnitude of work? Number 1. So number 1 has a large magnitude of work. Number 2 has a small magnitude of work. Now the question is the work positive or negative? Negative.
Positive.
Is it positive or negative?
Positive.
Positive.
It's menopause.
Wait, can't say.
Oh my gosh.
Like a fool on face.
Easy buster.
Looking like a fool with your pants on the ground. Gold in your mouth.
All right. They are both positive because we have a negative change in volume. Work is being done on the gas. Therefore, the energy of the gas goes up. So positive work and positive work. Okay, now, whoa, wait a minute. If the temperature change is the same and the internal energy change of the gas is the same, but the work is not the same, delta U equals Q plus W.
There was some.
Can heat be the same for the gases?
No.
No. Okay, because they have the same internal energy change, but not the same heat change. They have the same internal energy change, but not the same work, so they can't have the same amount of heat. Okay? All right, which brings us to, we've just figured out how to find work. So we know how to find pressure, volume, temperature on the graph. We have to be given number of moles. With that, we can find the internal energy change and the work. The only last thing then is Q. All right, if you were in chemistry class, you would use Q equals MC delta T, right? MCAT. All right, technically, if you're going to have a gas, you would use Q equals NCV delta T, or Q equals NCP delta T, because for a solid and a liquid, the objects don't change volume, and so technically, in chemistry, you're always using this one, constant volume specific heat. But for a gas, since the gas can change volume, there's actually two different ones, depending on whether you have a constant volume or a constant pressure. And we usually use N, number of moles for a gas, instead of the mass of the gas, okay? Otherwise, it's the exact same thing as before. The deal is that on the AP Physics exam, they have chosen not to put this on the exam. We used to teach it in physics, and chemistry used to teach it in chemistry, and it was on both AP exams. And it's been about 10 years ago now, they decided, well, we have overlap in the tests, so they got rid of this on the physics exam. So, could we find the heat using this? Sure. Will you ever be required to do it on this exam? No. So how do we find Q? Well, we have to kind of go through the back door. We have to find the change in internal energy, we have to find the work, and we have to find it from this equation. That's really our only tool, since we don't have to use this. Now, if you want to use Q equals NC delta T, and would like to solve it that way, you're welcome to do so. It's just you never need to. Okay? But you can if you want. So I'm going to erase that. We'll leave that for your next physics class. Actually, if you take physics C, you won't do that at all in physics C. And I refer you to page number 6 in your review packet. Okay, in that review packet on page 6, what you absolutely have to know about thermodynamics to pass the AP Physics B test. All right, here you go. Come on. All right, on page 6, there is a PV diagram with 4 processes, process A, B, C, and D, where the gas is changed somehow. And what I want you to do in that table is I want you to fill in that table and tell me what's the change in temperature of the gas, what's the internal energy change of the gas, what's the work done on or by the gas, and what's the heat exchanged to or from the gas. Tell me whether they're positive, negative, or 0 in each case. All right? So you just put a plus, a minus, or a 0. Okay? All right, while you're doing this, check your answers with your neighbor to make sure that you and your neighbor have the exact same answer. Okay. So, it looks like most of you are doing really well. You checked with your neighbor, everybody at your table have the same answer?
Yes.
Yes, 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 and yes? And yes?
Randy has to check with the gerbil.
The gerbil agree? Alright. Half A, temperature going up or down? So this goes, okay, because these are always in lockstep, right? Delta U equals 3/2 NR delta T, so whatever that does, right? Okay, work. Negative, because you're going to the right. Okay, wait a minute. Now, delta U equals Q plus W. If delta U is positive and work is negative, what's Q got to be?
Positive.
Yeah, not just any old positive, but a great big positive, right? We're going to put a great big positive there. Okay. All right, B, temperature change.
0.
0, so therefore 0. Work?
Plus.
Positive. Q.
Negative.
And not only is it negative,
It's a big negative.
It's the same size negative.
big negative, these two are the same size because if this is 0 and that's positive, that's got to be negative. So when you add them together, you get 0, right? Okay. All right, what about C? Temperature is negative, so that's negative. Work is 0, so therefore negative. Not only that, but these two have to be exactly the same because work is 0. Since work is 0, these two have to be the exact same. All right, D, we have a negative change in temperature, a negative delta U. Work is positive, so therefore this is
Negative.
but not just any negative, it's
Big
a
negative.
great big negative, right? Has to overpower that one. Very nice. You got it? Is it making sense? All right, with that little bit of knowledge, what you have right there in your head, you ought to be able to answer 1/3 to 1/2 of all the thermal questions. Okay? No, I mean like on the AP exam.
Oh, okay. Oh.
All right, so here we go. Okay, cycles. Okay, here's a cycle. A cycle is anything that begins at one spot, goes to another spot, and eventually ends up back where it began. Okay? So A, B, C, and D. And not that kind of cycle. Like hitting a home run. It doesn't matter. You start at home and end up at home.
On the cycle, you go 1. Yeah, single, double, triple.
All right. Here we go. Now, I want you to notice something. That delta T, A to B, is going to be positive. delta T from B to C is going to be, come on, work with me, negative. Delta T from C to D is going to be
Negative, because it's a pressure.
negative, right? Delta T from D back to A is going to be positive. What's delta T from A to B to C to D back to A? Zero. All right. Now, you can find that by finding every one of the delta temperatures and adding them all up, or by looking at it as a whole. Okay? So, lesson number 1, when looking at a cycle, any process that begins and ends at the same spot, you can look at it each piece individually, or you can look at it all summed up together. So for a cycle, delta T for a cycle always equals 0 because you end up back where you began. Now, that means that we have a delta U AB. We have a delta U BC. We have a delta U CD, and we have a delta U DA. And this one's positive, and this one's negative, and this one's negative, and this one's, this one's positive. But for the entire process, A, B, C, D, back to A, it's always going to add up to 0. Delta U for the cycle is always 0. Now wait a minute. If delta U equals Q plus W, and for a cycle, that's always 0, then what can we always say for a cycle? U equals W, but one of them's negative for a cycle.
The opposite.
They'll be the exact same size, but opposite in, exact same magnitude, but opposite in sign. Right? For a cycle, every time. Now, let's take a look at the work done. How about the work AB? Is that positive or negative or 0? It's negative because it's to the right. How about work BC? Positive, negative, or 0? 0 because it's vertical. How about work CD? Positive. How about work AD? 0. So when I add it all up, the work from A, B, C, D, A equals? 0. Oh, you fell for it. It's not 0.
It's WAB.
Is this negative and this positive the same? I want you to think in terms of area. This area from A to B is this area. This area from C to D is only this area. Or you can think of it in terms of, right here, I have a pressure times change in volume, but my pressure is large. And down here, my pressure is much smaller, times the same change in volume. So I have a large amount of work here, but less work here. Now, for those of you that are visual learners or have had a little calculus, okay, this red is a negative area. This green is a positive area. When I add the two areas together,
Negative.
you get the area inside the cycle only. Does that make sense? Okay, so this turns out for us to be negative, but it's the area inside the cycle. Okay? It's the area inside the cycle. That's kind of cool, actually, how that stuff underneath cancels out. Now, it doesn't matter what the shape of the cycle is. You can have a really bizarre shaped cycle, like there is a very famous cycle that looks like this.
Oh, wait.
Mustache.
Just like the thing that Batman throws. That's a magic lamp. It's a boom.
Or it could be Carnot cycle.
It's a mustache. It's definitely a mustache.
All right, that area inside is the work. Okay?
Definitely a banana.
Okay, here's the deal. Since we're not doing calculus in this class, we would not be able to find this area unless we could do some calculus. Okay? However, we can find this area because it's a nice geometric shape. What's that? That's correct. Just some geometry. So what kind of cycles could they give you where you could find the area inside? They could give you a circle. They could give you a triangle. They could give you a square. And they could give you combinations of those, right? So they could give you some shape like that or whatever, right? Some sort of polygon, right? But most likely it's going to be square, rectangle, circle, triangle. In fact, most of the time it'll be a square, rectangle, or a triangle. I don't know that I've ever seen a circular one. But it's possible. They could give you a circle. Because you can find the area of any of those inside. If they give you a crazy one like this, where they got a straight line here and a straight line here, and then they have a curved line here, like a hyperbola right there, then the work is the area inside, but we would not be able to calculate it directly, right? Not without using calculus. And they'd have to give us the equation of the curve, blah, blah, blah. We could do it, maybe, if you remember your calculus. But you won't have to use calculus ever. Okay? All right. So for a cycle, the work is the area inside. And wait a minute. If the work for this cycle is negative, then what's the heat for this cycle? Why?
Because it's negative, negative.
Because it's the negative of the negative. They're always going to be the same magnitude but the opposite sign. Okay? So here you go. In this particular problem, the cycle I've drawn right here, does the gas do work on the environment? Or is work done on the gas? So does the gas do work or is work done on the gas?
It's negative work, so the gas does work.
It's the negative versus positive gas.
The gas does work because it's negative. Because I have more negative work than I have positive work, right? So overall, the gas does work. Okay, so is heat added to the gas or subtracted from the gas?
Subtracted.
Negative.
If it's added, then it's bad.
It's added.
No,
It's
yes,
subtracted.
Our work is negative.
Versus of each other.
Our work is negative, but then we take a negative sign of it and that gives us our heat. So our heat is positive. So is heat added to or subtracted from the gas? Added to the gas. Now, here, this is really important. In a cycle, since you begin and end at the same place, that means you begin and end at the same energy level. So this should make sense. So if you're in a cycle and your energy doesn't change over the entire cycle, and the cycle does work, or the gas does work, that's going to lower its energy. So the only way to get us back to the same energy we started with was to add heat to it, right? What if my cycle goes the other way? What if my cycle goes, instead of going clockwise, what if my cycle goes counterclockwise?
Positive energy to subtracted heat.
Very good. In that case, work is done on the gas, but then, you have positive work on the gas, but then you have negative heat. So heat leaves the gas so that we stay at the same energy. Does that make sense? All right. Now, it won't make any sense to you at the moment, but the ones that go clockwise, just write this down. The the cycles that go clockwise are called heat engines.
They go clockwise?
PV. Okay? Clockwise cycles. That's called a heat engine. Where you have negative work or the gas does work and you have positive heat. Heat added to gas. Okay? That's called a heat engine. Alright? By the way, it's called a heat engine because you add heat to the gas and then the gas does work for you. That's what its purpose is. That's what you have in your automobile. You add heat to the engine, to the gas inside the engine by exploding gas vapor. It explodes. It adds heat to the gas. And then the gas does what? It expands. It does work by moving the pistons. The pistons move your tires, move the alternator to generate electricity for the lights, for the stereo. Okay? That's a heat engine. You want electricity for these light bulbs in here. You burn coal. You burn oil. You burn natural gas. Or you use nuclear. All of those are heat engines. What do? They generate heat. The heat is put into the gas. The gas expands. It does work. And that generates electricity. So you add heat to do work on the environment. True. All right, a windmill is a little different, and a solar cell is different. Okay, they do not operate on a heat engine cycle. All right, the opposite of a heat engine, PV. If you go counterclockwise. And for those of you with digital watches, this is clockwise. This is counterclockwise.
Thank you.
You're welcome. For those of you that have grown up with nothing but digital. Counterclockwise. So, lefty loosey, righty tighty, right?
I always say that when I'm done.
I'll do that when I'm
Okay, when you have this is called a refrigerator. Did I spell that right?
It's a D.
Fridge.
F-R-I-D-G.
DG. That's right, refrigerator. Is there? I think there is a D. Yeah, I think it is. I think there is a D.
No, yeah, because it's fridge.
All right. Now, for our refrigerator, you have positive work. So the gas, work is done on the gas. And heat leaves the gas. That's called a refrigeration cycle. Okay, now, this is kind of weird, but a heat engine in reverse is a refrigerator. I'll explain more later why that is. But in a refrigerator, you put work into the gas to make the gas lose heat, to cool things down. I'll explain more about that a little bit later, but I just want to show you that everything that's clockwise is a heat engine. The work is negative, so the heat will be positive. These add up to be 0. So they add up to be a delta U equals 0. Over here, counterclockwise is a refrigerator. Work is done on the gas and heat leaves the gas. So delta U equals 0 still. Okay? So we use these to drive our cars and generate electricity. We use these to cool things off. I don't know if you realize this or not, but we live inside of a refrigerator right now.
The air conditioning?
Yeah, because of the air conditioning. The air conditioning is really a refrigeration unit. Okay? And we're living inside of a great, big, ginormous refrigerator.
It's ironic we have a refrigerator inside a refrigerator.
That's correct. It is a bit ironic. Okay, now let's go and talk about some of the specific parts of the cycle or processes that have special names. By the way, everybody, if you are one of those people that likes to look at your book during this, or as I go over this, and then you like to look at it in your book, the thermodynamics chapter in your book, do not look at it. Okay? I command you not to. And the reason why is because the sign convention in your book is the opposite of what we have. It's not wrong, it's just opposite. They use the exact same words, but just so that you know, they call work this way the opposite, and they call this work the opposite. I won't even say it because I don't want to mess you up. And then they use this, delta U equals Q. Instead of saying plus W, they add minus W. So it all works out. It all ends up being exactly the same, but the sign conventions are opposite for work, and it will mess with your brain when you're learning it. So stop looking at your book if you're looking at your book for this.
Mr. Carter said that if you're looking at your book, you're going to fail.
Well,
Because I am out chemistry.
you may not. This particular chapter, they changed the sign convention in most physics books so that it matches up with the sign convention for thermodynamics in the other sections of science, like chemistry and in biology and all that. But some of the books still have the old sign conventions. So, okay, here we go. PV diagram. Okay, we've already talked about this one. What did we call this one?
Hyperbola. I answered first.
Okay, but that's the math name for it. Let's give it a physics name. We call it ISO. What does ISO mean? Same or single or one. Iso-Rooney? What?
Yes.
I know that from basketball. Isolation.
All right. Shh. Okay, ready? Okay, isothermal. Isothermal. Hey, come on. We're just going to finish up this a little bit. Hang in there. Isothermal means one temperature. So delta T equals 0. Therefore, delta U equals 0. Therefore, Q equals negative W. Right? In our equation, because delta U equals Q plus W, since delta U is 0, Q and W will be the same, but opposite signs. Okay? Same temperature. All right, there's another one. One that goes back and forth like this. Iso pressure. Isobaric. Baric. Did I spell that right? B-A-R?
That's right.
I have to look. Oh, 1 R, sorry. Isobaric.
Like a barometer.
Yes, like a barometer. Okay? For if you've ever listened to the weather and they talk about barometric pressure. Baric, or barometer, has to do with pressure. So isobaric meaning one temperature.
Yeah, I was going to say.
Meaning one pressure. Okay, now there's nothing in particular fancy about this one except it's really easy to find the work for this one because the pressure stays the same, so it's just a constant pressure times the volume change. For this one right here, it's hard to calculate work because the pressure's changing. Yeah, you need calculus technically to find the work for this one. Okay? All right. Now, these processes can go either direction, right, left. Okay, and then we got another one. Isochloric. Same chlorine level.
Isochloric.
You're cheating.
Isochoric, also known as isovolumetric, or sometimes referred to as a constant volume process.
We are just so smart.
Either way, that's the easiest one.
Yes. By far, this is the easiest one to find work for because work equals 0. Therefore, delta U equals Q every time. Now, there is one more special process. This is an important one. It looks like this. Now, it looks a lot like a hyperbola, except it's going to be steeper. Okay? Now, how do you tell this one from a hyperbola? Or this one from an isotherm? The way you tell is you would look at two spots. So you'd look at this spot here. Yeah, and you look at this spot here, and you see, look at the PV values, and see if the PV values are the same. If the PV values are the same, it's an isotherm, probably. If they're not the same, it's definitely not an isotherm. All right, this one is called... All right, can you pronounce it? Adiabatic?
Yeah.
That's pretty close.
Adiabatic?
Adiabatic. Adiabatic. And that's pretty good, though. Usually somebody says adiabetic. Adiabatic. Okay, adiabatic. Adiabatic means Q equals 0. No heat flow into or out of the gas. Therefore, delta U equals work. All right, now, you have to know these terms. Yeah, because there will be questions on the test. If you don't know these terms, then you won't get them right. So you're going to have to memorize these 4. Not that bad. Okay, let me give you an example of each one. A constant pressure process. Okay? Here's a constant pressure process. If you have a cylinder with a piston inside, the piston is free to move up and down. Okay? And then you take that and you set it on a stove. If you set it on a stove, you're going to add heat to the gas. But as you add heat to the gas, what's going to happen? It's going to expand. And as it expands, the heat goes in, the temperature goes up, the volume's going to go up, but the pressure's going to stay the same because it's going to be able to expand, right? Okay, so a constant pressure process, this is going to stay at 1 atmosphere the entire time if it's free to move. Okay? Kind of like a balloon. If you take a balloon and put it in a refrigerator, it'll shrink. If you take it out, it'll expand back out. It's kind of like that, except a balloon, as it stretches out, the pressure actually goes up because it's the stretchy balloon pulls in on it.
If it has this constant mass on top of that with no
Yes.
friction.
Yeah, something with a constant mass on top. Hey, let me finish, everybody. We've got a few minutes left. Okay, an adiabatic process. No heat transfer. There are 2 ways to get this. Number 1, if it's real fast. Okay? If you have a process that's real fast, like for instance, if I took this piston and I shoved the piston down real quick, did I do work on it? Yes. Will the temperature of the gas go up? Yeah. And will the pressure go up? Yeah. What happens is there's not enough time for the temperature of the gas to leak out because I did it so quick, right? Actually, you can do this. I should bring mine in. I have one of these where you can shove the piston down so fast that what's inside of it will light on fire. Because there's no time for the gas to leach the heat out, for it to flow out. So very fast process, or a process that is really well insulated. So like for instance, if I had a gas inside of a cylinder and I just insulated it really well so none of the heat could escape. Okay? So either very fast or really good insulation. Okay, an isothermal process. Okay? PV equals nRT. Almost anything you do to a gas and it's going to change its temperature, right? So the only way for you not to change the temperature of the gas is if the process is real slow. Like for instance, if I push this cylinder down real slow. Yeah, and the gas heats up, but at the rate that it heats up, the heat can escape. So it stays the same temperature. So isothermals are almost always really slow processes. And isochoric is real simple. Here you go. You've got a cylinder or a can. You seal it up so the can can't expand or contract. Ta-da! Constant volume.
Wait, what?
You have a container. Here you go. I'm going to take this and I'm going to put it in the refrigerator. Now this thing will actually shrink, right? The plastic. But if I have a container that has solid sides that can't move, I can put it in the refrigerator. Will its temperature change? Will the pressure change inside? will the volume change? Because it's in a container that can't change volume, right?
Except one expansion.
Yeah, but compared to the change in size of the gas, we'll neglect that.
By the way,
So constant volume process is one that can't expand or contract. Okay, our test is next week, Thursday.
I'm sick, so you can wait. I'll get sick.
No, I won't, because I'll take it out.
Well, I hope you don't.
All right, we have no homework. What I'd like for you to do, though, is in your review packet, I want you to read pages 9, 10, 11, and 12. 9, 10, 11, and 12, so you can get ready for next class.